Hi everyone, my name is Hannah and I'm the event coordinator at Manaaki Whenua Land Care Research. Before we hand you over to Christine, I'm going to run through a couple of technical slides to ensure that your experience with us today goes as smooth as possible. You'll notice that you have a control panel at the side of your screen. If at any time this collapses, you can bring it back simply by clicking the orange arrow button. If you're having sound issues and you can see my mouth moving but can't hear a word I'm saying, please grab the PDF in the handout section. This has instructions to resolve this quickly. The audio panel is where you see where the sound plays on your computer. Select the drop-down arrow to select your audio output. During the presentation, if you have any questions that you want covered in our Q&A session, you can do this via the chat panel throughout today's session. You will notice it is pretty small and it can be hard to read other attendees' questions. Select the pop-out icon and drag this to make it as large as you want. You can also use this feature if you are having technical issues to ask me questions. Questions asked by the audience will show as anonymous and in a green color in the chat panel. If I respond to you, this will show as red. Now over to Christine to introduce you to our High Flyers session.
Kia ora and welcome to our, I think it's our 14th LINKOnline webinar, and thank you for joining us today. My name's Christine Harper and I'm the Stakeholder Relationship Manager for Manaaki Whenua based in Wellington. My role today is really just to manage the questions at the end. So John is going to speak for about 20 minutes, and I would encourage you to put your questions into the chat box as soon as you possibly can. So that we can see them and have them prepared. If we don't get to your question, don't worry. We will see all of the questions and respond directly to them and register the responses on our website as well. Today I'm delighted to introduce John Dymond, one of our senior researchers and the leader of the Advanced Remote Sensing Aotearoa research program. This program helps us to develop new smart ways to use a variety of data sources to inform other research and national data sets such as the Land Cover Database. Over to you, John.
Good morning, everyone. This presentation is about the Advanced Remote Sensing of Aotearoa program. This is a 5-year research program that is funded by MB, and I'm the leader of this program, and there's quite a large team of scientists who are contributing. So just to start off with a very brief review of remote sensing in New Zealand. So 20 years ago, this was the state of play for remote sensing, where it was difficult to piece together satellite images because of different sun positions, different view positions, and different atmospheres, so that it was very difficult to get a homogeneous mosaic of satellite images. But over the last 20 years, we've been looking at standardizing images to a standard sun position, a standard view direction, and atmosphere and topography, so that we're now able to standardize images to a product like this, which is a flattened product with a standard sun position and view direction, so that what you're looking at is the reflectance of vegetation, which is a function of the vegetation alone and not other parameters. Being able to standardize images like this, you can produce national mosaics, which are ready for making land cover maps. And this is a mosaic of a whole summer period, 2015 and 2016 on the right-hand side. And on the left-hand side, we have a picture of where the pixels, which satellite images the pixels are coming from that form the mosaic on the right-hand side. So you can see that a lot of cloud clearing is involved to produce this mosaic on the right-hand side. So typically we have used one snapshot of a mosaic to produce a land cover map. For example, the land cover database, we would produce a mosaic for one summer to produce the land cover database one particular date. But coming up to just recently, the last few years, a new satellite has been launched, Sentinel-2. So Sentinel-2 has 13 spectral bands, 4 at the 10 meter pixels and 6 at 20 meters. And the great thing about Sentinel-2 is that we get repeat coverage of New Zealand every 5 days, because there's actually two satellites. There's Sentinel-2A and Sentinel-2B. And this is providing an unprecedented amount of data for New Zealand. So we're now able to get so much data that we don't have to rely on just one date to produce a land cover map. While this is a great opportunity, it presents problems. And some of these problems are that it's very difficult to remove the clouds. When we're just having that one date mosaic, we manually drew around clouds to identify cloudy pixels and not to be used in the mosaic. So that's what it was like on the top right hand side there. That's the manually cloud cleared image. But when we're using Sentinel, we're using many more images to produce the mosaic, the cloud-free mosaic, and you can see that we've got fewer clouds in the automated one. But this requires new techniques, and we've had to develop these new techniques which use T-mask cloud clearing, which uses an initial parallax method and also an object-based cleanup of cloud shadow pairs. So this method is an improvement on what's being provided by the European Space Agency. It's difficult to produce accurate maps of vegetation. So in this program, we're using this triple paradigm, where we're combining temporal analysis, vegetation structure, and extensive plot data to improve the accuracy of maps. Excuse me. So we're exploring the use of drones to get extended plot data. So we have drones and we're flying standard RGB cameras, multispectral sensors, and also hyperspectral sensors, which have several hundred spectral bands. And we also have a LiDAR on board the drone as well. We use terrestrial laser scanners on the ground, and this gives us detailed information about subcanopy tree structure, and we combine that with the LiDAR information on top from the drones and get a lot of detailed information that extends our plot data. LiDAR information is becoming available in New Zealand, and this is very useful for making maps of land cover. And here is the part of the Wellington region divided up into LiDAR tiles. So Wellington has been covered now in LiDAR at 1 meter, well, essentially at 1 meter size, 1 meter resolution. And I'm just going to zoom in on this small tile here. There are 8,000 of these tiles in the Wellington region. I'm going to zoom in on this small tile here and just show you what's possible with LiDAR. So this tile is covering some indigenous forest in the Rongorongo Valley. And you can use LiDAR information to automatically map crown heights and also the tops of trees, tree tops and their heights. And this is a graphic of a canopy height model, which is the difference between the ground elevation and the canopy elevation. And we've coloured up the height of the canopy height model. The colours in the dark red are all those areas that are higher than 30 metres. And just overlaying the crowns that have been mapped from the LiDAR on top of the canopy height model. And once you've got those crowns delineated of the individual trees, and you can overlay those crowns on top of the point cloud model, those are the individual points in the LiDAR. and we can now make better use of the point cloud information to characterize the structural detail of individual trees. And this research has been published in this paper here, and we've done a regional-based inventory of all of the trees, all the tall trees in the Wellington region, and it's very interesting to note how many there are. So we found that there's 286,041 indigenous trees in the Wellington region that are greater than 30 metres tall. These are very tall trees, and there are even many giant trees over 40 metres tall. There are 7,340. So we can basically identify every single tree in the Wellington region using this technology. Temporal analysis is now possible using Sentinel-2 imagery, and this is an example of using temporal analysis to map beech masting. In 2018, this was a major beech masting event around New Zealand, and we looked at the yellowing of the beech forest and the visible bands of Sentinel-2 to make maps of beech masting. So these red areas are all the areas where the beech has got excessive flowering and will turn into seeds later, which will unfortunately cause an explosion of rats and mice and will require extra pest control by DOC. So this information is very useful for DOC to prioritise their pest control. So that's the North Island. And this is the South Island, and you can see that all the red areas are the areas where there's excessive beech masting. So most of the beech masting is occurring north of that beech gap there. But there are some down in Fiordland, and this is the inset of Fiordland down here. As I said, temporal analysis is used to identify this excessive beech masting, and this is a graph that's demonstrating how that's done. So on the y-axis here, we have an index called the yellow index, and we have dates along here. So you can see that this, as we go through the year, typically this is the normal cycle of yellowing, this yellow index on beech forest. Does sort of a sine curve. So the grey areas denote springtime. And so in 2018, in springtime, that's the normal yellowing. There was a period for a couple of months where the yellow index was very, very high. This is due to the red flowers, red beech flowers. And so we measure the distance between the yellow index and the normal expected yellow index, and that's a measure of the beech masting. We're also using temporal analysis to map the extent of beech, and that map that we had before is based on quite old data, the New Zealand Land Resource Inventories, based on fieldwork, quite general. So we need a more detailed, more accurate map of beech, and so we've used the temporal analysis of the Sentinel-2 image to produce this national map of the extent of beech forest. So the yellow areas are the areas where we have more than 25% beech in the forest, indigenous forest. We've been developing remote sensing methods for detecting stress in kauri trees as well. And we use LiDAR and WorldView 2 to map the kauris and also the stress. And in the Auckland region, we're currently setting up a baseline of kauri stress detection, and this is the a map of the individual large trees in the Auckland region that we've just started to work on. Again, temporal analysis is very useful for mapping shrubland types, and here we're looking at the proportion of manuka in shrubland. So the colours here are indicating proportion of Manuka, so those areas with a very high proportion, 90%, you can see down the eastern side of the Aotearoa here. That's where most of the shrubland is mainly Manuka, and this is of great interest, of course, to beekeepers. Over on the Wairarapa coast here, tends to be dominated by Kānaka. And so we're using the different flowering times of the Manuka and Kānaka to identify these proportions. So pasture productivity is also a parameter that we can get out of temporal analysis. And so this is a map of pasture productivity of every paddock in New Zealand, the tonnes per hectare per year that is produced. And just zooming in on an area in the Canterbury Plains, so you can see that every paddock is mapped for the annual pasture productivity of that paddock. Also use temporal analysis for mapping bare ground. So bare ground controls soil erosion, and so the use of winter forage grazing during winter often produces bare ground, and so we've made a national map of paddocks that have got bare ground over 20% bare. So we've done the winter forage grazing in winter time, but we've also looked at the bare ground that's been associated with forestry activities. And this is just a demonstration of looking at that temporal analysis. So we've got a paddock here that has some vegetation on it, and some animals are introduced and start that strip graze, so the animals are grazing from right to left. You can see that strip is expanding until the whole paddock is bare, and this is at risk to soil erosion. We've also used LiDAR. So we've combined the structural information in LiDAR with Sentinel-2 to improve the delineation of indigenous forest types. So we're now able to map 6 different forest types. So they're up on the right-hand side there. This work has been published, and so if you want to read more about the details of that, you can refer to that work. So the implementation pathway for this program is through the land cover database. So this is the structure of our program here, which is, as I said before, it's divided into that triple paradigm of temporal analysis, vegetation structure, and new ground data. And that information is integrated to develop improved layers of the land cover database. And in LCDB 6, these improved layers will be rolled out in addition to LCDB 6. That is the plan. The land cover database version 5 has just been released in February, and you can now access that through our LRIS portal. So the information for that is here. It's also released through our environment and our web map surface. So these are the proposed new data layers at the moment that will come out with LCDB 6. So we can have an extra layer for indigenous forest classes. And we intend to get over 20 indigenous forest classes for that layer, and that'll be useful for biodiversity and pest control. We also intend to have a layer for shrubland classes, over 20 shrubland classes we intend to produce, and we think that'll be useful for weed control and the honey industry. Also a layer of indigenous grasses for biodiversity management. So planning to produce a spatially detailed woody vegetation layer for pest control and soil conservation. We intend to produce a pasture productivity layer, and you saw an early version of that for agricultural management, and a monthly bare ground map for soil erosion monitoring, and also showed you an early version of that. Also intend to produce a new wetlands layout for biodiversity management. So I think that's a very brief review of our program, and so I think I'll stop now and invite some questions.
Thank you very much, John. That was really interesting, and I can see the advances that we've made over recent years. Just a quick reminder to people that we did run one of our webinars on LCDB at the time that it was launched a few months ago. So we will put a link to that in our follow-up email so that you can review that webinar if you missed it when we presented it. We've got a great number of questions, and I know we're not going to get through them all, so apologies, but we will be responding. First of all, I wanted to check in on a couple of questions around kauri trees. John, can you tell us what are the indicators of stress for kauri trees? Were you looking at colour, or were you looking at canopy height for that?
No, it's colour. Especially that they lose their greenness.
Okay. And I've forgotten who asked this question, but what would it cost to map all the kauri trees in a region?
We would like to know that ourselves, so we're working through that at the moment.
Okay, so that's one of those watch this space.
Yes.
But it's great to get the question because it helps us to know what's important to you out there. We've got a number of people also asking about the pasture productivity, and in particular, how do we measure pasture productivity? What is it that you're looking at?
Well, the ground data is basically from published data from pasture cuts, and so people are cutting the grass under an area that's been excluded from stock, and so it's just basically the amount of grass is produced, the mass of the grass is produced per hectare. That's how it's measured on the ground.
And from the satellite side? From
the satellite side, we look at the median NDVI is quite a good indicator of the average annual pasture productivity.
Okay. Jim McLeod is asking us, is pasture productivity likely to be available on a regular basis?
Not at the moment. So that layer is a mean average. And so basically it's the average over many years. So it's unlikely we were producing information on a weekly or monthly basis at the moment.
Okay. Right, now we're going to go back to trees for a little bit. How do you distinguish a native tree from an introduced tree?
Well, at the moment we use masks to do that. So we use the mask that in the land cover database, which is a map of indigenous forest types being separate from exotic forest types. So that's our basic breakdown at the moment.
Okay. And maybe you've answered this at the same time. Layers for exotic cover would be hugely beneficial for the forestry industry. Have we any plans or intentions to develop a layer for exotic land cover?
Right.
I think they mean trees.
Yeah. Well, I mean, the exotic forestry is mapped reasonably well in the land cover database. So just as the present classes. So that's probably sufficient.
Okay. Right. Trees again. Can stored carbon content be estimated from the information in the land cover database or other information that you might be, more sophisticated information that you might be getting?
Yes, the LiDAR information is a good indicator of a total carbon that is stored in forestry. And LiDAR coverage for New Zealand is coming reasonably quickly. So I imagine that in about 3 or 4 years' time, 90% of New Zealand will be covered in LiDAR information.
Okay, let's move on to wetlands, another very hot topic I know for lots of people. Which data is used in wetland mapping, and when is that wetland map expected to be available?
Well, we're working on combining 2 different databases. So the land cover database maps wetlands to a particular standard, but there's another database called the Waters of well, it's the WONI database, and so that has a different type of characteristic. So we're working on combining those two together to provide a revised extent of wetlands. That's the one that we'll probably be releasing.
And will our wetlands layer detect wetlands down to half a hectare?
Yes, I think it'd be reasonably close. It's basically theoretically it's down to 1 hectare, so it's not far away from half a hectare.
Great, thank you. Now this one might be a little bit different, but from the satellite imagery that you see, is it possible to map algal content of rivers and lakes?
I think it probably is possible, yes, but we haven't been looking at that aspect. I imagine that some of our colleagues in NIWA are looking at that.
Okay. Now we're just going, probably our last question here. Can you please clarify indigenous grasses? And
Probably
do you use the mask?
grass. Sorry,
Okay.
what was the last part, Christine?
Do you use the mask to distinguish between pasture and indigenous grasses?
No, not at the moment. So we're talking about tussock grasslands as being the indigenous grasses, and no, we're not using the masting of the tussocks at the moment, but we will look into it.
Okay. Well, we've got time for one more, I'm afraid, John. What
Okay.
can be distinguished along the coastline? In particular, can you identify mangroves, erosion, or encroachment due to sea level rise?
Yes, well, certainly. Yeah, no, mangroves are quite clearly seen, and obviously the extent of the coast is very clearly seen. So yes, we will see all those things.
Do we have a category for mangroves specifically in LCDB?
We do.
We do. Oh, great.
We do.
That's good to know. Thank you. Okay, your answers are so good and quick, John, that we've still got time for one more. So,
Okay.
can you please explain the monthly bare ground for soil erosion monitoring?
Can I explain it?
Yeah.
So basically, well, at the moment we are looking at every paddock. So whenever we have an image, a cloud-free image, we are estimating the proportion of bare ground in every paddock. So that's the basic information we are getting. And so for any paddock, if it has 10 cloud-free images through a year, then we'll have 10 bits of information saying what is the proportion of bare ground in that paddock. That's basically how we're doing it.
Okay. Look, I think we're still getting questions coming in, but we probably need to wrap it up here for today. We will come back to everyone who's asked a question, and we will also put some Q&As up on our website along with the presentation after the event. So I'd like to say a big thank you to everyone for attending today. It's been great having you with us, and a huge thank you to John for taking us through this information that obviously so many of you are interested in. Keep in touch, watch this space. We'll be telling you about our next webinar over the next couple of weeks. Many thanks and goodbye for now.
Goodbye.